Okay, so basically, last time what we did was we began the topic of quantum physics, and we discussed why quantum physics is needed, and how is it different from classical physics, right? So we briefly talked about that, uh, and so as we move forward, we'll understand more in more depth why is that so. We talked about the fact that quantum physics or quantum mechanics is it's not a theory like we have electricity and magnetism, oscillations, uh, a theory of matter, sometimes also called condensed matter physics, uh, and all of those are theories, right? Gravitation, for example, uh, and so quantum mechanics is not a theory, it is a framework, which means that you can apply quantum mechanics to electricity and magnetism, to a condensed matter physics, as in matter, the physics that deals with matter, and you can apply it to gravity as well, and all the other theories. They can be seen in the framework of quantum physics. Uh, then we talked about some of the frameworks, and one of them was the Newtonian mechanics that we have been seeing since the beginning of the course. That is what we have been working in. Now we're moving to quantum physics or quantum mechanics, which is also a framework, and we'll see things in this framework, in the framework of quantum mechanics. So then we talked about a photon, right? And we'll cover that. What is a photon? The idea of photon, where does it come from? What really is a photon, and everything we'll cover in this video. But in brief, I said that it is packets of energy. So one photon is a packet of energy, uh, and then you could have multiple photons. So if I shine a laser beam of light, suppose I turn on a laser and the beam points in this direction, this beam is made up of multiple particles like this. So I can, so there's one particle here, then next to this there's another particle here, and you get the idea, right? So on. So this is made up of all of these photons, right? So photon is also a particle. Then we talked about laws of determinism, and we'll continue from here today. So the very basic idea that there is loss of determinism, as in you cannot completely determine or accurately determine both the velocity and the position of the particle at the same time, because of the fact that the electromagnetic waves are quantized by the concept of photon. So when I say light, right, light is the same. When I say light, I just mean electromagnetic radiation. Light is just one uh, small part of this entire electromagnetic radiation, but we are usually familiar with light, and it's small, and so you can say it very easily. So we just say the word light and do not say electromagnetic radiation, right? Anyway, so because this is made up of these packets of energies, if I have a particle and I want to see it, so this is my particle, and it's sitting stationary. The room is entirely dark. So when you enter the room, you cannot see this particle, right? Because the room is entirely dark. You can, if there is no light, and by no light, I don't mean that there is only a small amount of light or anything, but it's completely dark. So if it's completely dark, then how can I see what's inside the room, or at least let's say this particle? You'll just take a laser or a light or torch and shine it on that particle. Now, suppose, again, we're not talking about macroscopic particles, but microscopic subatomic particles. For example, it could be an electron. For example, this particle is an electron. You want to see that electron, what you do is you throw an electromagnetic wave, a photon, usually represented with the symbol gamma, is thrown onto this electron to observe it, right? So when the photon is thrown here, some of the energy from the photon is absorbed by the electron, and then the rest is reflected back to your eye, right? So it comes back to your eye, and when it hits this electron, what it does is it transfers energy to this electron. Some of its energy is transferred to the electron, and so the electron moves. It changes it could change its direction. It really starts to accelerate, right? It changes its velocity. What does that mean? So as soon as I observed this electron, again, observation, you can observe things by throwing something at them. In this case, we throw light at our particle to observe the state of the electron. This is sometimes also called in quantum physics the measurement problem, right? So you can never really know the position and the velocity both at the same time of the particle, right? So if I want, for example, if I shine a photon on it, the position changes, right? So maybe I can measure its velocity, with what velocity it starts to move, but I cannot measure its position. And same goes the other way around as well. So this is what we did so far. Is there any question from any of this? Any questions?
No, sir, it's clear.
Okay, all right. Okay, so okay, we'll move to the concept of a photon in much more depth. So let me start it with this thing. Okay, so very early in 1860s, right? Maybe it was 1865 or something. There was a physicist who goes by the name of Maxwell, right? And Maxwell conjectured that light, what we see, is really an electromagnetic wave. What does that mean? That it is a wave that is propagating fluctuations of electric and magnetic fields. What does that mean? We have already seen electromagnetism, and so if this is an electric field, wave for an electric field, and this is the direction of travel of this electric field, let's call it V, the magnetic field will always be acting perpendicular to this. So the magnetic field lies in this plane. Let's make this a bit big. Okay, so the magnetic field lies in this bottom plane, while this is the electric field, which is perpendicular to the magnetic field. So this altogether is an electromagnetic wave, and it's propagating, as in it's moving in some direction with some speed. So well, a lot of experiments happened and everything, and then all of those supported this idea of that light is an electromagnetic wave. So it was proposed in 1960s that light is an electromagnetic wave. Now everyone was pretty sure that this is how it is. It is just a wave, right? It's an electromagnetic wave, which means light is just a wave. But later experiments were done. One of the experiment which we'll talk about is the photo emission of electrons, or you could say photoelectric effect. And there were some experiments done on black body radiation as well. But let's talk about photoelectric effect. We'll talk about it in a bit in detail, but for the sake of this argument, I'll just tell you what it means is, suppose if I have a table or a metal sheet, right? And of course, we know that this metal sheet would be made up of electrons. Electrons live inside the metal sheet. That's what makes this metal sheet. So it is just really a lot of electrons in it. What happens is, if I shine a light on it, given that this has enough energy, we'll talk about this as well, but given the fact that it has enough energy, it is capable of spitting out an electron from this surface. So it is capable of emitting an electron. That's why photo emission. Photo as in light, electromagnetic wave, and emission of electrons, because electron is being emitted. So given enough energy to this photon, it can spit out an electron from this metal sheet. This energy that I'm keep saying depends on a lot of things, but it really depends, majority of it depends on what material am I talking about. If it is some well, it's not a right word to use, but I'll use it anyway. If it's a very hard type material, then you would need a higher energy of this electromagnetic wave to emit the electron. We'll come back to this in a bit, but then this experiment that was done was a problem for the idea that light is a wave, right? Because how is it possible that a wave striking an object is releasing particles, right? It was, and then there were some problems coming from the black body radiation as well. We will not talk about it right now in detail, but it's just that a body radiates, right? It radiates heat or waves. Now, this features of the photoelectric effect. So let me just bring it over here. Right. Now, this idea of photoelectric effect, we needed to really explain this, what is happening. And Einstein did that, where he said that in a light beam, energy comes in quantas, right? Again, that is the idea of a photon. So if I'll just bring this back down. So this light beam, the energy is in form of these photons. So these photons carry energies, and they are little packets of energy, and they make up a light beam. Now, which means that the beam is composed of the packets of energy. So what does that mean? That Einstein really implied that electrons are particles, right? They're particles, point-like particles, which carry some fixed amount of energy, right? So, well, Einstein himself found this idea disturbing, and he was never in the favor of this whole quantum mechanics. But this is how it really was. Now, it took a lot of time for scientists to accept that light could behave like a particle, but there were a lot of experiments done. There was one experiment done by the scientist called Crompton, and he really confirmed this, proved the fact that light really is a particle. Now, okay, so let's come to the idea of a photon in energy. So as we said that each photon of visible light or electromagnetic radiation carries very little energy, which means a small laser pulse can contain billions and billions of photons, right? And how do we detect these photons? One way is just by looking at them. Our eyes are a very good detector of photons, and the idea is that if you have an entire darkness room, a room that is completely dark, you'd be able to see light if there were only as little as 10 photons hitting your retina. So you would be able to detect detect that there is some light. So your eyes are very sensitive to light, and they can easily detect as little as 10 photons can also be detected. Now, I keep saying that, I wrote electrons are particles. I meant light or photons. Right. So when I say a particle, to a light as a particle does not mean that how we have been talking about particles before, that they were point-like objects which carried zero energy. Which carried zero size. There was no definite size. So this was a point, and it was a particle, and this particle was specified by its position x and velocity v. So these two coordinates could completely define this point-like particle, which has a zero size. Its position is determined as x and velocity as v. But when we're talking about quantum mechanical particle or quantas or quantum particles, they are really packets of energies and momentum, right? And they're the most basic ones, fundamental, you could say fundamental packets, right, or particles, which means that they're not composed of any other smaller packets. So these particles are quantum mechanical, which means that they are packets of energy with some momentum. Okay, so this energy, let's see what does it depend upon. by doing experiments, we verified that this energy of a photon depends only on the color of light by an experiment, right? So by when we did an experiment, we changed the light, the color of the light, and the energy of the photon would change. So how can the color of light change, right? So what I want is, I want an equation that determines this energy. How can you change the color of light? If you remember, you have the spectrum VIB, VIB, GYOR, right? And these are multiple colors, right? Where red has the highest wavelength. So wavelength is increasing in this. So red has the highest wavelength, lowest frequency. Violet has the lowest wavelength and hence the highest frequency, which means that these lambda and frequencies are differentiating between red, orange, yellow, green, blue, indigo, and violet, right? So what does that mean? That means that this energy E is dependent upon wavelength lambda, right? And as it turns out, it is sorry, not lambda. It directly depends on the frequency f, and it depends inversely on lambda, which should be clear because this relation that it's inversely dependent upon lambda is derived from this one, that it is directly related to frequency, because we know that velocity speed of light is f lambda, which means that f is just c over lambda. So if I put this in this one, then you see that it is really just 1 over lambda. So it is dependent inversely on lambda, which means for a higher frequency, you would have a photon, a packets of higher energies, right? And so if I consider an example of, let's pick a single color, suppose you have green photons, then all of the green photons will have same energy. Why? Because their frequency would be the same, as their wavelength is same. So all green photons would carry same energy. And so you can also increase this energy in a light beam while keeping the colors same. How can you do that? Can you suggest anyone? If so far I said that it depends on the frequency or and on the wavelength of these photons, what energy they would be carrying. If I want to increase the energy of a beam that I'm throwing at the surface, what is one other way that I can do that? Okay, so I'll answer that. If I have multiple photons, so for example, if I just throw a single packet of photon, I'll just now draw it like this, on a surface, compared to, so suppose this is my surface, and then let's compare it to another one where I throw 1, 2, 3. So this one combined has some energy E1, and this one has some energy E1 plus E1 plus E1. So 3 times E1, right? So obviously 3 times E1 is greater than E1, which means that this one has now the thing was that these photons were of same color still, but by increasing the amount of photons that I throw at a surface, I can increase this energy, right? Because 3 times, it would become 3 times E1 if initial for a single photon the energy is E1. So is that clear? Any questions from that?
No, sir, it's clear.
Okay. Okay, so now we'll talk in detail about the photoelectric effect. Okay, so again, the idea is that you have a metal surface. Suppose this is your metal surface, and what I do is I throw an electron onto it, sorry, a photon onto it, so which is just any electromagnetic radiation. I throw that on it, and what I observe is that it kicks out an electron from the metal surface. So one photon is responsible for one emission of an electron. So the ratio is 1 to 1. And so what I did is, again, I incident some light onto this plate, and the result was an emission of an electron. Now, this thing only happens under certain conditions. And one condition is that there is some specific amount of frequency that is required for this photon, so it is capable of spitting out an electron from the surface. Because electrons in this surface are bounded to this surface, all these electrons, they're all bounded to this surface. Of course, and it is done by some energy. So they're bounded to the surface by some energy. And you need to provide it enough energy so that you can overcome that bounded energy, which we'll call work function. And if you can overcome that energy and throw a higher energy photon at it, then it is able to remove the electron from it, because it will then break that barrier of the energy. So there is a certain amount of frequency that is required, and that frequency is called the threshold frequency. Again, this frequency, the concept of this one comes from the fact that this phenomena only occurs a photoelectric effect. So I'll just call it P. Well, let's write it entirely. Photoelectric effect only occurs for some specific frequencies, and that frequency is known as threshold frequency. At this frequency and above this frequency, you're capable of releasing or removing some electrons from the material or metal surface. Okay, so the bounded energy of these electrons that are bounded to this metal surface is what I said I'll call the work function, right? So the concept of work function is that it is the minimum energy that I need to give a photon to remove an electron from the surface of the metal, right? So it is then the minimum energy of a photon to remove an electron. And you can see that it would be different for different materials, because for different materials the boundedness of the electrons to that material is different, right? So for example, for a certain type of material, you would have a higher work function, while for some other type of material, you could have a lower work function. So it is completely dependent on what material that we're talking about. The work function is usually denoted by the symbol phi, and this symbol phi, the work function, is equal to mathematically some constant h, right? Because again, it depends on a frequency. This frequency is the threshold frequency that we talked about initially, right? It is again the minimum energy of a photon that is needed to remove the electron from the surface, which is coming from the threshold frequency. So if I get rid of this proportionality and convert it into an equality, it becomes some constant h times f naught. H is known as the Planck's constant, right? And so let's go back and let me write an equation for energy from this one, these two relations that we see. They say that energy is equal to some constant h times f. This h here is also the Planck's constant, and this form of the equation is h and times c by f, right? Because c by lambda, because what I did here is, in place of f, I replaced using this equation, c over lambda. So h is a constant that comes from removing the proportionality and converting it into equality, and c comes from this one, f equals c by lambda. So this is h c by lambda. So these are the two equations that we have for energy of this photon. So anyway, coming back to this, any questions so far?
No.
Okay, so is the concept of emission of electrons clear?
Yes. But like, sir, I
Okay,
don't get
so
why we're emitting electrons.
sorry, why?
I mean, we're emitting electrons, so won't that substance itself lose its electrons and become charged again and again?
I mean, of course, yes. So if you're throwing for light at it, it is releasing electrons, and of course the surface would get charged. In fact, this concept of photoelectric effect is can be